Welcome back. In this video, we're going to talk about logic gates and binary algebra. Binary algebra and logic gates become important because logic gates are the foundation of how we build digital systems that make decisions and eventually leads to computer systems. We're going to start in our conversation. We're going to start by introducing and learning what logic gates are, what do they do, and why we are interested in. So in this video, we're going to focus fundamentally on an AND gate, okay, which usually is represented by this symbol. If A is an input, B is an input, and C is the output, the way we write it is that C is equal to A with the dot B. The dot indicates an AND function. So that's an AND function. That's one of the fundamental gates that we have. The other one we look for is the OR gate. And that gate basically is C. If input is A, B, and C, then we use a symbol of a plus symbol, which is an OR symbol, B. So that basically say A or B. And as the name implies, both A and B have to be true or 1 in order for C to be true. For A or B, if A is true or B is true, both will be acceptable. But either one of them being true causes C to be true. Now, we use something called the truth table, and I will, not to make a mess of this picture, we'll wait till we get there before we talk about it. But the truth table is what describe what they do very specifically, so it leaves no confusion for anybody listening to us. The other gate is this. This gate is one of the very few gates we have that only has one input and one output. And let's say A is the input, C is the output, and this is the shape we usually try. This is called a knot. Sometime you may hear it referred to as an inverter, or very rarely, but still as a complementer. All of that means the same thing. If A is true, C would be false. If A is false, C would be true. So it just does an inversion. Now, formally, we are supposed to represent this way. A is inverted with a dash on the top. Now, if you're using a text editor, that's kind of hard to do. And then the other option is to use this curly bracket, this thing for A, this little kind of a wavy looking thing from the keyboard to indicate is right above tab, if you're wondering where that symbol is, indicate an inversion. The easiest one for us to use, and what we're going to use in the text from here forward, is we use a prime to indicate A is inverted. So that's going to be our go-to symbol. But just remember that all of these indicate inversion. Now, there are these other gates, and you're going to use blue. If you look at it, this is basically the same as an OR gate and a NOT attached to it. So if you think about this NOR gate, is basically an OR gate with a NOT attached to it. So that's all it is. Sometimes that's kind of nice to have. NAND is an AND gate with a NOT gate attached to it. And then, so exclusive OR is kind of a fun thing to talk about, but we don't spend a lot of time. If you're interested, there are documentation we can go through, but its job is if input is A or B, and this is C, C will be true if neither one of these guys is true. So if they're not the same, if A and B are different, C is 1. If A and B are the same, C is 0. It's an interesting parts, and we can talk about it at maybe a later date. But for now, we're going to primarily spend our time understanding this, and this. And once you understand how to read the data sheet for the AND, OR, and NOT, then the NOR, NAND, and exclusive OR becomes just a little variation on the theme as far as that's concerned. So let's dig in a little deeper into each one of these and get to know all the resources that are available for you to extend your knowledge of this device. Okay, these are very well established parts. So there are many companies who make these things, and so there's a bit of a variety in how they describe it. But the functionality, it doesn't matter who you buy these things from; it's going to be exactly the same. But the way they describe it might be slightly different. So let's start first with our NOT gate. That's a it is the simplest gate, and the symbol, as we said, looks like this. And and the way we represent input is A, output is C, and we say C output is equal to A NOT. And then a truth table. This is if you're first time seeing a truth table. Truth table, the way you do it is you create this cross, and then on one side, on the left-hand side, you put all the inputs, and on the right-hand side, you find out and put the values of the output. So on the input side, I only have one input, and then what I do, I put all the possible value of A. A is a binary number, so the only thing it can be is 0 and 1. Since I have one bit, the total number of possibilities 2. So I've written it. And notice how I would like to do it in order from 0, 1, 2, 3 if possible. This way you don't miss anything. And we know the function of this is to take, if A is 0, make the output 1. If the input is 0, make the output 0. So that's pretty much what a NOT gate or an inverter does for you, okay? Now, if you want to buy one of these and build it, you can go to a part which is either 74 LS04, or it's equivalent with the new technology of CMOS 74 HC04. If you're doing it in a classroom and we give you to do it, I like to use LS because it's hardier, so you touch it, your electricity in your body doesn't damage the part. If you're doing it for mass production, or we are doing simulation where that is not a problem, like in using Tinkercad or something like that, or some other simulation scheme, then we'll use this one because that's kind of the most common things that's used in production, because it's high speed, and if you're doing it in manufacturing, you take all the precaution not to damage it. But if you're handling it in your hand in a classroom or a lab environment, this would be a more safer thing. But as far as we're concerned, they're exactly the same. All the information is the same. Now, this is great. This is kind of a quick review of it, but if I want to use it, where do I go to get information to use it? So in order to figure out, you can search for it. You can literally search for 74 LS04, and all the companies that produce it comes up, and datasheet is basically the manual, technical manual for that chip. The easier for the class, all the parts we use in the class are placed in engrcs.com. So if you go there, click on the component specification and go and find 74 LS04. It's a hex. The part, when you get it, it's basically physically looks like that. We don't really physically draw these in our schematic. We always do it logically. So in this case, if you go farther down, it tells you A is the input, Y is the output, and they use high and low instead of 0 and 1, which is fine. And then they'll tell you how parts are connected to each other. One A is the input to one Y and all that. So when you go up here, and literally, I'm going to expand this out and draw into it so you can kind of see what we're doing. Now, you got to be careful to make sure that you're looking at the correct part. We are using 74 parts, so the part we need to be looking at for our purposes is this one, okay? And what they're basically saying, they says this part is a hex inverter, which means it's got 6, hex means 6, has 6, and this is how they are hooked up to each other. So there's one there, the second one is here. They're independent of each other. Third one is here, and you can kind of see the picture. Fourth one is here. Now, be careful if you get in a rhythm of saying pin 1. So when you draw this in a schematic and you want to use it, you don't draw this box to physically show it. What you do, you draw it like this, and you say, okay, this is, you name this unit 1 or unit 2 or whatever you want to name it, and then you put it in here, and then you say, okay, I'm using pin 1 and pin 2. This way, you don't have to physically draw the shape of the part, but rather you can logically represent that I'm using what you're basically saying, I'm using this one, okay? And that's all there is to it. And if you're using this physically looking at it, the way you know which is pin 1, you see that I'm gonna have a notch on the device, and pin 1 is gonna be to the up next to the notch to your left hand side, okay? And then we're not gonna spend a ton of time on this, but if you ever need to, I wanted to make sure you knew it. But for the stuff we do in the class, you don't have to worry about it. There are lots and lots of descriptions of what this part is all about. And let me go ahead and make it a little smaller so we see everything. So you go down and it gives you all the characteristics of, what actually, how it's designed. Remember the transistors at the beginning and the previous like 2 or 3 section here is they're showing you how the transistors are used inside this chip to build your inverter that you're using. And depending on which part you're using, they might be slightly different from each other. It talks about the different packaging, what type of voltage it needs, and all of those kinds of the data that you may need. For one thing I forgot to mention, and I'll go back up here to mention it, is when you are using these chips, almost all of them will require you to connect the ground and VCC. That's 5 volts. VCC is 5 volts for the parts we're using here. So that's important, that before you can use this part and this part does anything, you have to connect that to a 5 volt and you have to connect that to a ground before it starts working, okay? I think that's about all we have for this. Now, so let's go back and see if we can remember what all the things were that we had talked about. So that's what the NOT gate is all about. The other gate we want to talk about is it's called the AND gate, and the AND gate is simply drawn like this. Again, A is the input, B, you can name it whatever you want. And this is an AND. And as we talked before, C is written as A, or A with a dot, B, that's a representation of AND. And once again, we do a truth table. Remember, we put the input on this side, output on this side. So output here, input here. In this case, we have 2 inputs, A and B. We have 1 output, C. So the way we do that, 0, 0, 0, 1. I'm writing a binary value of 0, 1. See how I'm going in order? 2 and 3. And then what I'll do is say, okay, and if you AND a 0 and a 0, you get a 0. The 0 and a 1, you get a 0, 1 and a 0, you get a 0, 1 and a 1, you get a 1. AND means that both are 1 in order for the output to be 1. Okay. And the parts, if you're interested in reading about the part is 74 LS08, okay, or of course, or HC, LS or HC are the same, 74 HC, 08, just a different technology used. So if you want to go find that, we can go back again to engrcs.com. Let's go ahead and clear all that. Okay. All right. Go ahead and resize this thing before I bring it over. So. All right, so let's go ahead and go back. And then we go to the for input AND gate, which I'm sorry, 2 input AND gate, which is right here 74 LSO8 or HCO8. And this is how it's set up. There are 4 of them independent of each other. Once again, in order to use this, you have to connect pin 14 and pin 7 to 5 volts and ground. VCC is 5 volts. And then you can use this pin 1 and pin 2 as an input, 3 is an output for this one, and on and on. So you have 4 different ones in here. And of course, the same as before, there are all kinds of description beyond here. For now, we don't need to get too deeply into it. Just as long as you know which pin is the input, which pin is the output, you're good to go. And then last one before we leave, we'll look is the OR gate, and OR is the 74 LS32. So if you look at over here, this is what it looked like, and all the truth table is provided here, symbol is given to you. And then the last one, I'll do this before. Exclusive OR is the other one potentially if you want to look at it. As we said before, it's just like AND and OR. You have to pin 14, you have to connect to 5 volts. Pin 7, you have to connect to ground. You got 4 separate units in here. So you can use either any of them or all of them. And so if inputs are the same, you get a 0 out, low, 0, false, they're all the same thing. And if they are different, low, high, or high, low, the output is high. So if the inputs are different, you get a high or 1. If the inputs are the same, then you get a low. Doesn't matter whether it's high or low inputs. As long as they're the same, you get a low. Okay. So that's pretty much it of the parts we've talked about. And this one is, it ends with an 84. It's called exclusive OR, and this is here is the symbol for it. Great. So where we are now. So where we are is the last one. And let me go ahead and write this so we have looked at this as well. So a AND gate, the last piece we said, comes in. I'm sorry, it was OR, I think was the last one. OR is the last, and we already did. OR, A and B are the inputs, C is the output. This is the truth table. So always you need a truth table to make sure you know how it operates. And inputs are A and B, outputs on the other side are C. We write everything in order: binary 0, binary 1, binary 2, binary 3, and that's all the possibilities we have with 2 input. If you have 2 input, you have 4 possibility, and we have captured that. So, or the difference, and the way we write it is that C is equal to A, or, which is a plus sign, B. So 0 or 0, if they're both 0, the answer is 0. If any of them is a 1, you get a 1. Okay, so that's a 1. So those are the functions that's available to us. Okay, so now what does that mean? That means now I can build circuits that makes decisions. Okay, but before we get into doing that, let's talk a little bit about expressions and how what an expression means, and then we'll come back and do some designs in the future chapters. So let's go ahead and try to see if we can write some expression and make sense of some expressions that we have here. So let's say someone writes a function, and typically we write a function. We say this is a function of A, B, C, and so what this is basically saying is I have a device. This is called a system diagram. What I'm drawing right now is called a system diagram. And when you write something like that in this function looking thing, you're basically saying F is the output of the system, and the input to the systems are A, B, and C. That's all it says. Okay. So it might say, it doesn't say what's inside. When you write the function like this, what you're telling the world is that you got A, B, and C are the independent variables. In math, we call them independent variables, but in here we call them inputs. And F is the result, is the output. So you might have a simple function of A or B, okay, and C. Let's just and C not. Let's say that's it. So what is that? So this is a function. if inputs are a certain thing, sometimes it's one, sometimes it's not one. So how do we describe what this thing does? Then we, of course, use the truth table to do that, okay? So this is called the algebraic, this is a binary algebraic relationship. And the way we make sense of what it does is we go to truth table to figure out what it does, okay? So let's go ahead and do that. Let's do a truth table for this. Remember, as we've talked just a little while ago, a truth table is basically a cross form. And on this side is all the inputs to the system. And on this side is all the outputs, okay? So in our case, we have input A, B, and C, and only output we have F. You can have multiple outputs. You don't have to stick with one output. You can have many expressions if you want to. So this one is 3, which means 2 to the power of 3 is 8, which means there are 8 possible combinations of A, B, C. But we're going to be very careful to make sure we cover all of them. So what we're going to do, we're going to say this is 0, 0, 0. That's binary 0. That's binary 1. This is binary 2. This is binary 3. This is binary 4, 5, 6, and 7. Oops. And 7. So now we have all the possibilities done. Now what we got to do, we got to take that function we have, which is F is equal to A or B and C naught. So what we need to do is for each one of these rows, we need to figure out what the output is. Okay. So how do we figure that out? Well, we figure that out by going through and plugging in values of A, B, and C into this function. So if A is 0, that means 0 is ORed with 0, ANDed with C naught, which is 0 naught. 0 or 0 is 0, ANDed with 0 naught, which is a 1, is still a 0. Okay. So, and then we keep going down the list, and I would encourage you to do it for yourself so you get comfortable with that. You can put the video on pause and go through and fill the rest of these tables and then start it up again to check to see if I'm doing it right or whatever. So the next one, of course, will be 0 as well. And now I'm going to go to the next one. The next one we're going to do is A is 0, fine. B is 1, which is great, or 1, that's nice. ANDed with 0 naught. Okay, 0 naught is a 1, 0 or 1 is a 1, 1 and a 1 is a 1. Okay, and you can go through and do the rest of it. I'm going to do a little quickly so you can check yourself. I believe the next one will be 0, and the next one would be a 1. And the next one would be a 0. And let's do one more completely so you can kind of follow in case you are not getting the same answer I'm getting. So for example, the next one says A is 1, B is 1, 1 or 1 is a 1, ANDed with 0 naught. 0 naught is a 1, therefore the answer is 1. On this one, I know the answer is 0 because it's 1 or 1, ANDed with 1 naught, which is a 0. Anything ANDed with a 0 is 0. So this has got a truth table. You don't necessarily need to write these. You just have to show what the answer is. Okay. Now, if someone gives you, so we're pretty much done with the key concepts we want to cover in this video. But if someone comes to you and says, hey, I've got 2 functions. Can you tell me if these functions are equivalent or not? What you do, you say, okay. So for example, and then this is an assignment you have to do it. So let's say you says, okay, you got a function x, y. You don't have to, you can make up variables as you wish. This one, it says we got an input of x and y and z, output is f. one output is F1, and that is X or Y or Z. And then the next one, it says, oh, F2 is X, Y, and Z, and that one is X not or Y or Z. And they're asking, are they, well, that's kind of too obvious. So let's make these and, for example. And they're asking you, are these equivalent? So the way you do that, you say, okay, no problem. I'll just do a truth table. And my output, I have two output now. I have an F1 as an output and an F2 output. Much like we went through the previous exercise, you go through for all the possibility of X, Y, and Z and find out what F1 and F2 is. If in any instant, in any row, F1 value and F2 values are different, you say they're not equal, okay? So that's what you do. 0, 0, 1 again, 0, 1, 0, 0, 1, 1, 1, 0, 0. What I'm doing, I'm going through all the binary count. It's really important. Your truth table will not be correct if you're randomly putting values here. It has to count 0, 1, 2, 3, 4, 5, 6, and 7, okay? Then what I'll do, I'll go to F1 and say, if everything is 0, what happens? You say F1 is equal to 1. And then here, you say, okay, if everything is 0, what is this? And then, of course, this unfortunately will be 0. Not fortunately, actually, this is easy because my very first row says F1 is 1, F0 is 2. So you can simply come in here and say F1 is not equal to F2, and you're done. Okay. So let's do a quick review, and I'm going to use the course material to kind of walk through it, so we just make sure we see everything the way it's done there. We talked about NOT or inverter. We said we use a prime to indicate that. We talked about OR gates and how the symbols and everything is. We talked about AND gates and what the symbols are, what the truth table is, and all that. And then exclusive OR, we mentioned it. Here it is, the truth table for it. And binary expression, we talked about the fact that you can write binary expression and you can do a truth table, which one side is the input, the other side is the output. And you go through basically plugging these values into those. And remember, you're doing binary, you're not doing regular arithmetic, okay? So that's really important. 1 or 1 is written this way, and the temptation is to say, because it's written like a plus, 1 or 1 is written like a plus, your temptation is to say it's 2, which is not true. 1 ORed with 1 is a 1. But that's initially when you're getting used to this concept, that there's a temptation to do decimal arithmetic on it. But just remember, this is binary arithmetic. Okay. So you go through and do that, and talks about priorities. When somebody's written an equation, equal sign has the highest priority. Parentheses is next, not, or, and much like you have it in a regular arithmetic, you know, multiply, divide are higher priority than plus and minus. That same concept exists here, except not is the most important one. Happens first, and happens next, or happens next. And if you want to force certain operations, then you put a parenthesis around it to force the stuff inside the parenthesis to happen first before you go forward. Okay, so we'll that brings us to the end of this video of talking about what is an expression. We talked about truth tables to describe what an expression's values are at different values of input. We looked at 3 other gates. Of course, there are hundreds of gates, a variation on the AND and OR, that as you get in more into this field in later classes, you will explore them in much more in depth. Thanks for listening.